All right, here we go. We are on path integration part 7. What are we doing today? Oh, we're finishing chapter 9. We're finishing chapter 9 of Shred Nikki. We're going to be seeing some really cool stuff. I got some Feynman diagrams we're going to go over. We're going to evaluate the Feynman diagrams. We're going to talk, now listen, the first 5 minutes are going to be a little intense, okay? Nobody panic. This is going to be good, okay? This is going to be good. The first 5 minutes of this are going to be intense because we're just going to lay out a bunch of stuff. We're going to be talking about what we did in chapter 9. And then we're going to start seeing some diagrams and we can make it a little bit more reasonable, a little more tolerable. We have path integration part 7. If you guys made it this far, you've made it to part 7. Good job. Welcome. Welcome to part 7. I don't even know how many they're probably going to be like 9 or 10. And I think we're going to call it. I think that's about as much as we're going to be able to milk out of this path integration. Okay, let's do a refresher, okay? Now this is going to be the
I was asking for my friend.
This is going to be the refresher of chapter 9. Now, like I said, don't get intimidated, okay? There's going to be a lot of things that look scary, but we've seen them all before. We know what they do, and we're not going to be, they're not going to push us around, okay? No way, okay? So, we start with the Lagrangian. What we started with in chapter 8 even was the free Lagrangian, okay? So, we saw it again in chapter 9, and we're going to leave it up and we're going to go over it a little bit. But we have the free Lagrangian, which looked like this, right? And this is how we started doing our path integration stuff for a particle. We had a free particle. We needed to get to the propagator, which was basically just saying that a particle was going to go from, a ground state to a ground state, okay? And there was nothing too spooky about it, right? This was our Lagrangian that was basically established that free particle. Well then, now we wanted to do we know particles aren't free, right? Because particles interact. Okay, so we know that this is general, right? This is general for a free particle. All right. So we know that this is too general, so we need to figure out some sort of way that we can talk about a particle interacting. So we introduced Phi-cubed theory. Clackless. Clackless. And that is 1/2 z phi of delta phi, or d phi minus, and this was just a very general Lagrangian, and the point of it was just to make it so that we could use interaction theories and stuff. I mean, we know particles interact, right? We know that they interact. So now we have to figure out how they interact. And this was just a very generalized form of a Lagrangian that's going to tell us how particles are going to interact, okay? And this has a Hamiltonian density, right? A Hamiltonian. Of the following. And again, like I said, don't be too intimidated by all this stuff. It's not really, we don't need to know everything in these. We are going to be kind of breaking them down a little bit. We're going to kind of we're going to talk about the counter terms today. That's going to be the main point of me showing you this stuff, is we have to talk about the counter terms.
Wait, I missed something. Can you go back 5 months?
So this is the Hamiltonian density describing a free particle, or not a free particle, an interacting particle in the Phi-cubed theory where we had our interaction term. Okay, so now we have the Hamiltonian density and we have all of this stuff. And where is this going to leave us? Well, we need to talk about, we don't know how to deal with this Lagrangian, right? We only learned how to deal with this Lagrangian in a free field theory, right? So the goal is going to be, can we unpack this in terms of this so that we can extend on it and make it interacting. And we did that. We did all of that. And the way we did that was we had 3 Lagrangians. We had this one, and then we had the interacting one that looked like this. It had the interacting term, 1/6. Oh, geez, I wrote it wrong in my notes. Oops. I should fix that, or else I'm never going to fix it. So if you're following along with the notes, there's an error. The interacting term on the top of the second page, it's supposed to be 1/6, not 1/2. So if you're following along, you should fix that. And then Z, G, G, GG, no re, phi cubed plus the Lagrangian counterterms. Now, the Lagrangian counterterms are the one that's weird, right? Like, we know we need this. This is how we're going to extend the field. We know we have an interaction term because when we first did this in quantum mechanics, this was like episode 2 or episode 1. Then you can go and, what's going on here with my cords? What? You go to episode 2 or 1 and you can figure out that we extended the quantum mechanics right away into an interaction field theory so that we could get these terms down out of we get the functional derivatives down. And that's how we got the functional derivatives and the time ordering thing in like the first or second episode of this series. And so now we can handle this and this, and then the counter terms, we just said, okay, well, when we're starting with this, we have to get rid of these counter terms because we don't really know what to do with them. And so we just said, let's ignore these for now. And like today's the day where we say, okay, we're not going to ignore them anymore. We're going to bring them back. And what did that Lagrangian look like? Well, this was the counter term Lagrangian. We had the 1/2 z phi minus 1 times the derivatives of the fields minus 1/2 zm minus 1. And I told you that this stuff's going to come in handy when we have to renormalize. And like I said, this is what we're going to be doing today. Okay, so we have these Lagrangian terms. And then notice that if you do add this Lagrangian to this, so if you had this plus this, then you get back your original Lagrangian. Okay, that's the goal. Is if you add the counter terms to this, you get back to your original Lagrangian. So it's almost as if we can save it if we're careful. And we do have to be very careful, and we will end up saving it. So we have this. I just want to make a special note of this Hamiltonian. We're going to need it in a second. Notice this term in the Hamiltonian means that we need to be very careful about how these counter terms show up, right? These counter terms are going to have a role to play, and we have to make sure that they follow the Hermitian. They want this to be Hermitian. We want these terms to be Hermitian in the Hamiltonian, or else this is not going to be a physical thing. So let's start. So this is what we did chapter 9, okay? This is all of going back and saying, like, these are the things that we started chapter 9 with. And then let's talk about what we did last week so that we can set up for today, okay? All right, so what did we do last week? Well, last week, we spent a lot of time counting diagrams and canceling certain higher order diagrams, right? That was the goal, is we had to talk about all the symmetries. There's a lot of diagrams we had to count. We had to count endless amounts of diagrams. And we're going to get rid of even more diagrams today. And there's an infinite amount of diagrams, so you have to be careful about how many there are. Or you have to be careful about which ones you save and which ones you're allowed to cancel away. And there's all sorts of things that are going on that we have to be careful about. So we added we ended by noting the following. If we took our amplitude of the interaction, and that was proportional to exp of all of the connected diagrams, right? And then we said, okay, or we could take this z1 of j and set it equal to the exponential of iw of j, where iw of J was just all of the connected diagrams without the, hold on, let me double check this. Is all of the connected diagrams without the vacuums. Let me look at the actual wording so I don't screw you guys up with that. The vacuum diagrams are omitted. Okay, so which is to say that all the vacuum diagrams are omitted from the summation. Okay, so now let's continue to ignore. So we're going to keep going now. So now as we're starting today's stuff, let's continue to ignore this counter term thing, and let's see what just happens naturally if we don't use it. What happens naturally? And we're going to find out that we're going to get in trouble, and we're going to need to bring it back in. So let's just say that we want to find a vacuum expectation value of a certain phi field. So we want to find, so the goal for today is to evaluate the vacuum expectation value of a phi field using our new path integration, okay? So we can go ahead and start this calculation, and let's see what we figure out. So we have 0, phi of x, and 0, and it's basically like if you have the vacuum of space, how likely is it that a particle is just going to be there, either annihilating or creating? And the goal is hopefully 0. Like, you don't want that. So we're going to do one functional integral because we only have one field, or a functional derivative, right? And then we can rewrite this basically in terms of w. Oops, I don't know why I'm writing 0 here. What's it supposed to be? X. Whoops. And then we can rewrite in terms of W, our new notation of non-vacuum connected diagrams. And what are we going to get? What's going to happen? And we have, like I said, we have one source term, right? That's all we get. We're going to end up getting one source term because if you take this derivative of this, you're going to end up with the source. So we're going to be like, okay, well, what's the deal with the source? How do we find the source? Every time you take a functional derivative, you're getting rid of one of the sources, and there's two sources in this. So let's go ahead and take a look at some diagrams and figure out what's going to be left with one source. So looking at this, we can see that here we have two sets of diagrams, 9.3 and 9.4. Both of them has one source, right? And that's all we really need is the one source diagrams. Now, do you guys know what's the difference between these two diagrams? Well, the first one has one vertex, v equals 1. And the second three have 3 vertices each, right? See the v is equal to 3? Let's count them. There's one right here, there's one right here, there's one right here. So there's 3. This one, there's one right here, there's one right here, and there's one right here. And then lastly, one right here, one right here, and one right here. Okay? So we have 4 different graphs to consider, and this is only, again, only at a vertex 3. Okay, you can keep going with these and go higher and higher if you want. Hold on. Wrong screen. Okay, we're back. So let's go ahead and see what these diagrams looked at. We can talk about the diagrams. We have this one right here, and this one's called a tadpole diagram, okay? And they're technically all called tadpole diagrams, but this is for the diagram. This is what we have. It has one source. So if you take the functional derivative of this, you're gonna be left with one source. So what are we gonna have? We have one source here. And then this one is at order of G, right? Because we're gonna have one vertex, which if you guys remember from our Z, that means that there's gonna, because remember that I had that long Z thing for the Phi-cubed theory where we're gonna have every term was gonna get multiplied together, and that's where we got this, you know, E is equal to 2P minus 3V, where E is the external sources, P is the propagators, and V is the vertices, right? Let's just see some of these rules real quick. Well, if we have a propagator, then we're going to get 1 over I, and then the propagator itself, or what we saw to be the green function or whatnot, the extension from the Green's function. I should say it's the Green's function for a certain solution. And then I and the integral of d for x, j of x. And then the vertex is I, z, g times g. And then the integral of d for x. Now, these are our little Feynman rules for our little toy Phi-cubed theory. If we look at a diagram, we can identify the different parts of it, and then we can go ahead and build the amplitude, right? So let's go ahead and do that. Let's look at these. Let's look at this diagram. Is my camera in the way? Actually, I think I'm right above it. The camera is right above it somehow. So let's build an actual integral based off of our rules for this Feynman diagram. So we can look at well, we'll just get there when we get there. Okay. If we want to evaluate that again, so let's say, oops. Let's make sure we have our x in there. Then we can rewrite this as the following. Well, how many propagators are there? There's going to be 2 propagators, right? And 1 vertex. I think that's it, right? And 1 source. So we're going to have, so we write down 1 source, 2 propagators. Let me look at the book too. Let me make sure I have the notes correct too. I want to make sure I don't make any mistakes. Okay, very good. So for the first one, we're just going to have 1 vertex, 2 propagators, and 1 source. So it's going to look like this. And again, this is right in the notes if you want to follow along. And I did pull this directly from Shrednicki. Have IG integral d4y 1 over I delta x minus y 1 over I delta y minus y, because it's a loop, right? And then this is going to be orders of g cubed. Now remember what I said, this is perturbation theory. So the more g's we have, the smaller the contribution is going to be to the path. Why am I lagging so hard? So here we have our integral that will solve, the amplitude from going from the ground state to the ground state of this. But there's a big issue with this integral. And that means that the vacuum expectation value, or this, despite this term, this is going to be so small it's not going to matter. But we can actually get a real number for this integral, right? There's a real evaluation, a real number for that integral, and we have an issue with that. We're not supposed to get a number. This is supposed to be a 0 amplitude thing. You're not supposed to be able to just create particles in and out, because then you're going to end up having the vacuum expectation value and a particle. And like, where did that particle come from? Why is it sticking around? Why doesn't it just go away? And these are all very crude analogies of what's actually physically happening, but it's still okay to think of it this way, I think, in my opinion. And we need to make sure that this is in fact 0, okay? So we're going to introduce a counter term to make this 0. And since we have 1 phi here, you can bet that bippy of yours that we're going to introduce the following counter term. So we got to introduce counter term I told you it's going to be back, and there it is. And here's what we want. We want to introduce this counter term y of phi for the main purpose of making this equal to 0, okay? So let's erase everything and let's keep moving on. I think I'm going to want a full board for the next couple things we do here. Remember what I said about this y phi? Y phi is in the Hamiltonian, and therefore it has to be Hermitian, the Hamiltonian density. Therefore it has to be Hermitian, so that's going to be kind of important in the next few steps here. as we try to figure out how to take advantage of this counter term. And yes, this is the beginning of renormalization, if this is what if anybody is wondering. This is the beginning of what we're going to need for it. So we want to introduce y of phi such that if we take the vacuum expectation value of a single field phi, we'll get the following. We'll get I of y.
Wi-Fi is how it connect to the internet, you fool.
That's good. I like that. 1 over I delta 0, all multiplied by the integral of d4y, 1 over I, and the propagator from x minus y. Notice how we took this propagator, this loop propagator. Remember, this is for the diagram of just this. This is, of course, we'll have higher orders of g, but since this is perturbation theory, we're going to just ignore them because they're going to be very, very small. So in this diagram, we have two propagators here and here. This is a loop propagator. We have one vertex and one source. And this is what we're trying to evaluate. So this is the goal. We want this to be 0. If this is 0, then it'll take the whole thing to 0. And we can be happy about our vacuum expectation value of a single field being 0. So that means we actually have a value for the y. The y is going to be 1/2 Ig times this integral, and then plus, of course, some, oops, that was wrong. There's going to be some higher order diagrams for this as well. We can actually, because we're adding this in the same sense of adding an actual term to the Lagrangian, remember this is an actual term to the Lagrangian, we're going to have some diagrams. And the diagrams are, no, you're good, Jax, don't worry about it, I got them. And the diagrams are going to have a very certain shape to them, right? So we can say that there's going to be, this one's going to have a diagram that looks like this, and these are also in Shred-Nicky. I wonder if I can show you guys real quick, actually. No, I'm not going to. I've just drawn. So this diagram is going to look like this, where we just introduce this x to be some sort of vertice with one field attached to it, right? That's the nature of having a vertex that's y phi, is there should only be one field attached to this vertex. And then there's another set of these that looks like this. It's an order 3, and they could be of any kind that look like this. X, then you have another one that looks like this. Remember, like, a lot of particle physics is doing a lot of Feynman diagrams and kind of evaluating what each of them means. And if you are doing particle physics, you're going to be doing a lot of Feynman diagram stuff. So these would be higher ordered. These have 3 vertices, right? 1, 2, 3. 1, 2, 3. 1, 2, 3. Like, all of them have higher order vertices. They're going to have some coupling constant with them. In perturbation theory, that coupling constant is going to be cubed. It's going to be small, and we're going to get rid of it. Okay? You did it, NC. You did. Okay. But there's an issue here, right? Y has an I in it. The issue is that Y is supposed to be real. It's supposed to be real because inside the Hamiltonian, this has to be a Hermitian operator, right? So this is going to be a big issue, or the Hamiltonian should be a Hermitian operator. So this has to be real. So we got to figure out how to make it real. But let's not worry about that too much right now, because it's going to be a little bit more natural. But what that does mean is that this has to be imaginary. In order to make y real. So that's going to be the focus, is we're going to see if this becomes imaginary very naturally. And we're going to end up not being able to evaluate something, but this is something, we could do the evaluation of this on the one of the math days that we take after, where we actually look at some of these calculations more in depth. So like I said, this series is not associated with a university. This is just stuff that I do in my spare time. And after we get to the end of the material on path integration in Shred-Nicky, then we're going to spend a couple days just going over some of these mathematical things in closer detail. Okay. So let's write down what this is. Now this is a Green's function, remember, so it's going to be some integral of an exponential of e to the x minus y, except they're both y's. So it's going to be e to the 0. which means the integral is going to look like this, d4k divided by 2 pi to the 4th times this, the momentum plus the mass squared minus this small I epsilon naught that we had to introduce. And we have no idea, BT Assailant, welcome to the channel. Thank you for the follow. And we had no idea if this is imaginary. We have no idea if this is imaginary. But it needs to be imaginary, but we have no idea. We can't tell. What we do know is that at some large value of k, k being the momentum, at some large value of k, this becomes infinite. Or becomes divergent, excuse me. The integral diverges. That's going to be a big issue, right? And we call this an ultraviolet diversion. So at large k, so what? So at large k, this is divergent. And this is an ultraviolet divergence. Ultraviolet divergence. So we hear that term a lot. This is what we're talking about. Something like this happens. Okay, so because this is divergent, this is what we need to do. We need to make this not divergent. So we need to introduce another term. So let's introduce another term. Another term. And we'll call it the ultraviolet cutoff. Okay? And this is that higher ordered energy. You can imagine this being much, much greater than m. Okay? Much, much greater than any other energy involved. This is the cutoff. This is why we call this an effective field theory. Okay? Because we know that at some higher order of this, then there could be a different physics happening that's accounting for the fact that this is a divergent integral, right? That we don't need to worry too much about it because we know that ultimately that that we're going to be under a certain energy limit anyways. But we're saying that if under this energy limit, this works fine. But once we get to a certain energy limit, that's where we start to get these ultraviolet divergences and stuff. And we also do it in a way so that the cutoff can preserve Lorentz transformation of a propagator. And then we're going to write down what that propagator is now. So again, let me just reiterate what's going on here. We introduce this term because we need this vacuum expectation value to be 0. Okay? Because we don't just want like particles to be created out of thin air. Okay, start from the beginning. So we introduced, this because we want to make sure that the vacuum expectation value of a single particle is 0. We also want this to be real, so that means that this has to be imaginary, and this we've got to figure out if it's imaginary, but it doesn't even matter if it's imaginary, because it's going to be infinitely large, or whatever. And it's going to be divergent, so we need to make sure that this is not a divergent integral. And how do we do that? Well, we introduce a second term. We'll call it the ultraviolet cutoff, which basically say, okay, this is all going to work if we keep the energy level down. As long as we're not into a certain spot, and we're going to let that be big. We're going to let it be much bigger than m, but we're just not going to let it be infinity, okay? It turns out that you can actually allow it to be infinity too, and then there's some interesting things that happen, but I'm not going to get into that because I don't think I understand it very well. So our new propagator is going to look like the following. Instead of having this guy right here, we're going to introduce an ultraviolet cutoff, and we're going to get this. The integral of d4k divided by 2 pi to the 4th. And then this is an actual Green's function with x and y, so we need to make sure we have the exponential of I, k, x minus y, and all divided by k squared plus m squared minus I epsilon. And then we're going to introduce our ultraviolet term, the cutoff squared divided by k squared, plus the ultraviolet cutoff squared minus I epsilon squared. Now I think this is definitely something I'm going to do. This integral, I think it's definitely something I'm going to do when we do the math days after this. And try to like understand some of how these integrals actually work. Okay. So now, evaluating this integral, except for every other physics, or every other case. Well, that's effective field theories. And I mean, effective field theories work really, really well. And that's just something we have to accept, I think, that effective field theories work really well. And though it may be weird that we're introducing all this stuff to kind of save them, they work like super well. So I mean, like, who are we saving? Feels more like sometimes it feels more like we're actually saving our intuition by like saying that this stuff is a different way than it really is. When in reality, our intuition is the thing that's wrong, and this is just the way that it should be. So we can actually do this integral, and we'll do it at some point, I think. I think that'll be a good thing to do for the math day. But it's going to end up being the following. It's just going to be I16 pi squared times our ultraviolet cutoff, which I think the ultraviolet cutoff is squared. I think I have another mistake in my notes. It is. Good catch. Ultraviolet squared. So again, if you're following along in my notes, make sure that you square this ultraviolet cutoff. That is not the way it is in my notes. Well, it is now, but this is good because this means that if we let, oh, I'm sorry, this should not be what I wrote here. This is specific to, am I above chat? That's specific to that. I am above chat, sweet. Well, you often get to remove lambda anyways. Yes. I haven't got there yet, Justin. You're gonna spoil it. So the good thing is now we get to get this term. It is imaginary, so this is imaginary. Check, and that means that this is real, which is good. Which means we can plug it into here, and that means that it's going to cancel out this. This is going to go to 0. Our vacuum expectation value of one particle goes to 0, and that's good. So here's the clincher, okay? And this is what Justin spoiled for us all. And this is how we all get, this is specific to tadpole diagrams, right? This whole process is specific to tadpole diagrams. These eliminate tadpole diagrams in Phi-cubed theory, okay? So anytime you have a tadpole diagram, this is basically saying, get rid of it. We're done with it. So like Justin said, we don't actually need to think about this physically. This is technically it's an infinity. It gets brought into our equations, and it cancels away a different type of infinity, i.e. the ultraviolet divergence. And what we're left with are all diagrams that have no tadpoles in them. Like if you cut a line, then you're always going to have a source on either side. So there's a list of diagrams that survive. Let's, no loop for you. That's really good. Why have we not made a meme of that yet? So if we look at the diagrams that survive, Semphora, welcome to the channel. Thank you for the follow. Can I do it? Yes. Yes, I can. So there's a series of diagrams that survive all of this, if I can find them. And our tree boys are in there. We like our tree diagrams. Oh, here are those diagrams that are associated with the Wi-Fi. There they are. So no matter which way you cut a propagator, with a single line, you cut a propagator right here, you can cut a propagator right here, you can cut a propagator right here. No matter what way you cut a propagator, you're always going to have sources on either side. Therefore, there are technically what we call no tadpole diagrams in these, and these are the ones that survive. Notice the interesting ones that we've talked about before. Right here, right here, right here. These three right here are called tree diagrams. Those are probably the most important, and usually, I think they're the most, in perturbation theory, the most, the ones that contribute the most, I think. I think that's a general, what do you think, Justin? Is that general? I think that's general, yes. They contribute the most, just because usually they're the lowest level of perturbation. I think. Maybe that's wrong. But either way, that's the benefit of it. So, That's what we do. We have these weird things. We introduce this term, Wi-Fi. We introduce the ultraviolet cutoff to kill the ultraviolet divergence because we don't want these infinities. And that means that basically, in all of our diagrams, we don't ever need to worry about tadpoles. So they all go away. We never see this ultraviolet cutoff. We say, hey, these infinities exist, but we don't need to think about them. They're gone. They just get rid of the weird diagrams. And we're back to our good old reality of diagrams we can actually calculate and actually have some amplitudes of these probabilities. Okay. We have one more term to worry about, and that's the rest of the cutoffs. We know that this cutoff existed, or this, oh, I should get back to the board, huh? Jax isn't here to yell at me. Why is chat so small? So small. So we get back to, so yes, we introduce all this stuff, and then we don't have to think about it, and it kills all the infinities, all the bad infinities get to go away. And we have one more thing. We had this cutoff. We have to talk about the other cutoffs, or the other, not the other cutoffs, excuse me, the other terms in our counter term, Lagrangian. We know they're second order in our perturbation, or in our perturbation theory. So basically what we're going to do is introduce them as diagrammatic stuff. Being that they're second order in G, like that was something we did when we first started chapter 9, then we know that they're going to be some sort of vertex with two lines coming in and out of it. And then we'll understand the nature of them in a second. So A is equal. We're just going to do some simplified notation. So we know we have this term, right? Like that was something we had to think about. And we also have the other term where z of m minus 1 was another counter term that we have to think about. So now our z of j is the exponent minus I over 2 integral of d4x times 1 over I functional derivative of j of x times our minus a x squared plus, and these I'm pulling directly from the original Lagrangian. 1 over I functional derivative with respect to j of x. And this is all multiplied by the full z with the y in it that we just talked about and dealt with, okay? Now, these things, like I said, I'm not going to get too much into these. These don't have a ton of stuff going on. But this is the reality of what these do. We had the y of phi, and we had to introduce it. And these are also going to have a role to play. But like I said, they're going to be vertices, and they're just going to be little interactions in the vertices, okay? So basically what you want to do is just say, hey, in all of our diagrams here, let me show you the diagrams again real quick. In all of our diagrams here, we're just going to sprinkle every single diagram here will also have some sort of diagram, another diagram that has this vertex in the propagator, okay? So all propagators exist with these vertices as well as they exist without them. They're just more diagrams to think about, okay? Wait, I've ruined it. Can't believe you've done this. So yes, they're there. We have to count them, but they're not anything to shake a stick at or to shake your fist at the clouds at. Okay, it's just extra vertices that we have to make more diagrams of. They survive. There's nothing weird about them. Sure. So this is what we've got. We're finishing chapter 9 right now. This is it. Z of j. We found that this for Phi-cubed theory, so for Phi-cubed theory, we have found z of j is equal to the exponential of IW of j, where W of j is given by all connected diagrams. So all connected diagrams with no tadpoles and at least two sources. Oops, I don't know what that is. Sources, blah, blah, blah. And includes and includes these counter term vertices. Okay, so that's it. We have taken some infinite sum times infinite sum of numbers. We have multiplied all the terms together. Each term that we multiply together becomes an amplitude, which eventually, or which becomes, and it's given by a diagram. And we said there's so many, infinitely many diagrams, and then we've narrowed it down to the ones that really matter, and that's just these. Now, Helen, can't stay here today, but I want to say seeing path integration on Twitch is amazingly great. Oh, awesome, Helen. Great, thank you. Yeah, I love it. I love teaching it. And I'm glad people like to be here. Because like I said, nobody has to be here, and yet people still show up. Which is pretty awesome, if you ask me. Because that means people want to learn it, and that's super cool. Okay, so that's it. We've done it. We've written a Phi-cubed theory. Okay, we figured out the interactions. We've renormalized it. We got the effective field theory part of it. We've done it all. So now, what do we do with it? What do we do with this? What do we do with our knowledge of diagrams? So now we have an expression for this. Like, we know what this is. Or if we don't, then we can at least watch videos about it and say, hey, I think I was taught that or something. And we have an expression for that, and we need to evaluate the vacuum expectation value of two fields in a time ordering product, okay? So let's define this new propagator, and this is a little bit weird. I don't know why Shrednicki does this, but he's smarter than I am, so he has like a filled in delta. So let me see if I can try to do that. And that's going to be x1 minus x2. It's just a different style of propagator, and that's going to be the vacuum expectation value of the time ordering product of the field at x1, field at x2. Ooh, can I fit it? Yes! Just barely. So let's first say, for notation's sake, so this is going to be, we're going to carry this on next week, so for notation's sake, because I'm going to be writing this a lot, and I do this in my notes, and Schwartz does it in his book. This is kind of common, so we're going to say that the functional derivative, Ursula still survived. You can still see her. Right there, okay. And her red lips. Okay, anyways. The functional derivative, we're just going to call it this little delta with a subscript. And the subscript is, it's a j, let's do a j. J. The subscript is going to be for the functional derivative of j of x, xj. So now we're talking about a bunch of different x points in space, so we're going to be talking about the different the functional derivative of them. So then we have, let's write out our time ordering product as we know it to be from before. And this is the beauty of the diagrams, okay? This is going to be some functional derivative of 1, functional derivative of 2, z of j, evaluated at j equals 0, okay? And like I said, this is the beauty of everything we've done so far, is now we have the functional derivative 1, functional derivative 2 of... Wait a second, that's not right. Hold on, I think I have a... Is that really what he wrote? What he wrote? Where's Shrednicki? Oh yeah, that is right. Okay, never mind. I thought that was a mistake, but it's not. IW of j evaluated at j equals 0, and then we'll have the chain rule, so we'll have the I, or whatever rule this is, whatever derivative rule. Come on. The functional derivative IW of j. Wait, this is not. The functional derivative of 1. Holy smokes. Evaluated at j equals 0 times the functional derivative at 2 of IW of j at j equals 0. And then these are all 0 because these are 0 because the vacuum expectation value of just psi of x has to be 0. Like that was what we talked about before. If you were to actually calculate this, you would find you'd get this inside, and that has to be 0. Okay, so it's going to be 0. And we just left with this. functional derivative of 1, functional derivative 2, I, wj evaluated at j equals 0. But what did I say before? I said that under these circumstances, after some functional derivative, every time we attack this with, I shouldn't say attack, every time that we apply a functional derivative to this w, we are killing one of the, I shouldn't say kill, we are eliminating one of the source terms, right? So this w has these two sources around the propagator. We're going to eliminate the sources by using one of these functional derivatives. And by doing that, what does that mean? That means ultimately this will get us back to the propagator. So we can find out that on lowest order, okay, so on lowest order, if we go back to this picture really quick, imagine this in the Phi-cubed theory. Where is it? Where is it? There it is. Imagine this right here, this top, oh, sorry, wrong screen. This top left diagram, we have two sources, source 1, source 2. We have a propagator in the middle of them. And now we're applying this functional derivative twice to show that we're going to apply it at x1 and x2. And what are we going to get? Well, like I said, when you do this functional derivative, oh, I need to go back to the other screen. What am I doing? So when we apply this functional derivative twice, we're going to knock off both of those sources, and we're going to be left with just a propagator. Wait, let me make sure I have this right. Oh, it's right below me, and I'm still... Oh, he doesn't even write it down. Okay, so we're going to be left with just a propagator. So this is the only thing that's going to be left. So what we can say is 1 over I, and then this like weird delta that's supposed to include a bunch of things, x1 minus x2, for this particular case, is just going to have the 1 over I, the normal Green's function propagator, x1, x2, and some higher order terms in g squared. And since we are doing perturbation theory, we're only going to be interested in one of those terms. So it's basically like applying these functional derivatives is basically taking that top diagram like this. And each time we apply a functional derivative, we're knocking off one of the sources. So what we're left with at the end is just a propagator going from x1 to x2. And now you can start to see what the real Feynman diagrams look like without the sources. We are finished with path integration part 7 today. Next we're going to say, okay, like we don't want to do the sources anymore. Okay? We're not going to pay attention to the sources. We eventually want to get out of the sources. Like, you don't see Feynman diagrams with these little balls hanging around the edges, right? So next week we're going to be doing path integration part 8. We're going to see more of these diagrams. Interesting diagrams that are going to have all different shapes and sizes. We're going to lay down rules for the diagrams. And eventually we're going to get to the spot where we're comfortable using the path integration to write rules for Feynman diagrams. And with that, we'll have we'll have rules. So then what we can do is just look at some fields, write a bunch of diagrams, and apply the rules. I don't understand anything, but this is really interesting to watch. Awesome.